what we see on the screen here that you're showing. I think this is, Roy, this is your screen? Yeah.
While we wait, can all the participants, if you guys don't mind, can you put in chat where are you joining from?
Yeah, great idea, Ekta. We should probably introduce ourselves as well, eh?
Yeah.
That might be a nice thing to do. Do you want to start, Ekta?
Sure. So welcome everyone. So glad you all could join us. So I am an astronomer. I am a postdoctoral researcher in the research group of Brian Lemaux and Professor Laurie Lubin at University of California in Davis. And I study galaxy clusters. We will talk more about it in a bit. Currently I'm joining from my home in India. So welcome.
Thanks, Ekta. I can go next. So my name is Brian Lemaux. I'm a researcher, astronomer, scientist at the Gemini North Observatory, which is another one of the observatories on Maunakea, just let's say east southeast from the Subaru telescope, maybe a couple 100 meters. So we're up there on the summit as well. My job is partially to run the operations of Gemini North. So I observe with Gemini North. I try to get the best science out of Gemini North. So it's a little bit different. Our model at Gemini North is a little bit different than the model that's at Subaru. So in Subaru, and we'll talk more about this later, we applied to use these nights. And it was in fact Roy that was the one who was applying. And then it goes through a process where other scientists evaluate that proposal. And then we're awarded a certain amount of time on the telescope. So the last 4 nights we were awarded time on the telescope, and unfortunately the last 4 nights it's all been canceled. But on Gemini, we actually do something called a queue observing system, which means that scientists propose, and then we try to fit in throughout a half-year time period the best observations that we think should be taken. And so figuring out what defines best, and then how you take those observations, that's part of my job. The other part of my job is to do research. So that I do that with Ekta and with Roy and an international team of collaborators. So I'm joining from my house in Hilo, which is just down the mountain. And if you hear my baby screaming in the background, that's my baby screaming in the background.
All right, I'll go next. My name is Roy Gal. I'm an astronomer at the University of Hawaii at Manoa Institute for Astronomy. We have facilities in Hilo and Maui as well, but I'm actually in Manoa at UH Manoa, although right now I'm sitting at home. If you hear a little bit of talking in the background, that's my wife who's also working at night tonight. And if you hear kids, that's because one of my kids woke up and came in to talk to me. So we're astronomers are normal human beings too. Here at UH, I actually run our outreach programs, so that's why I'm participating in STS. But this also is my research group, or I'm part of this research group, I should say. So I applied for this observing time, as Brian said, and this observing time is time that the University of Hawaii has access to on Subaru because it's built in Hawaii. And we'll talk about the science some more later. If you were ever in Hawaii and engaged in outreach programs like public stargazing and things like that, you might see me there. And welcome everybody from all over, including some familiar, at least one familiar face. Hi, Paul.
Okay, I'm happy to go next. I did introduce myself earlier, but for those of you who were not on when I did introduce myself, my name is Jamika Marshall, and I am the Shadow the Scientist Coordinator. As Brian said, I am joining from Memphis, Tennessee, though I do live on the Big Island of Hawaii. I live a little bit south of Brian in Pahoa. And I have lived in Hawaii for, 9 years next month. And before being the coordinator for Shadow the Scientist, I was a colleague of Brian's at Gemini-N, doing outreach. And I am also very pleased to be able to say that I have worked with Roy during outreach on Hawaii Island. So I'm so glad to see all of you here. And thank you for joining us very much.
And so, Jamika, I'm not sure how much you said before I came on, but in case anybody's wondering why we're so calm and collected, or marginally so, it is because tonight's observations were canceled. So we found this out in the late afternoon, probably about 3 hours ago, Hawaii time. And this is due to very, very strong winds up on Maunakea. This has lasted for 4 days now, and it just so happens that our run, which is the series of nights that we have in the telescope, is 4 nights. And so unfortunately, we've been weathered out for the entire time. The really strong winds make it, along with the freezing temperatures, make it very difficult to even get up to the Mauna. So accessing any of the telescopes at this point is very difficult. They can do it during the day, but nighttime it's very dangerous. With 50 to 150 mile per hour winds and about 20 degrees Fahrenheit temperature, you have to look out for falling ice blowing across the road. And in fact, many of the sensors up there on Mauna Kea from the different observatories have frozen over or are damaged by falling ice and by the winds. One of the monitors that points towards the Gemini-N telescope from the Canada, France, Hawaii telescope, and I see that Roy has a picture up on the screen now of the kind of the orientation of Mauna Kea. So CFHT, Canada, France, Hawaii telescope is there in the top right, and then Gemini-N is just below that to the south. And then Subaru, where we're observing, is over to the west northwest. And so one of the camera that monitors Gemini from CFHT is actually tilted 45 degrees and is kind of hanging on by a thread at this point. And nobody has had the ability to go up to the dome and actually, yeah, there it is, and actually fix it. So hopefully that sticks to the inclement weather, and they can go up there and fix that when things calm down a little bit. But at Subaru, the dome, the main shutter of the dome, so a telescope is protected by this giant dome. So that was Gemini-N that Roy was just showing. And there's a shutter that opens up that allows the telescope to see towards the sky, so it blocks light normally. They could not open the shutter due to the really high winds, and that's important because they have to check for ice and other debris on the shutter during the daytime. And so they haven't been able to do that for 4 days. So unfortunately for 4 nights, things have been canceled. And in fact, this is the, I think, 24th or 25th night in a row that there's been no observations on Mauna Kea. And this is a new record for Hawaii. So unfortunately, that's what's going on with astronomy right now. But we still can definitely show you a lot of pictures and things. We can talk about our observations that we're planning on taking. So yeah, that's the context for these observations. And unfortunately, all we can do now is we're not taking new pictures, which is what we'd be doing tonight if things were going well. I don't know. So Roy, you have the screen up here that shows one of the Subaru observing screens. So we're actually able to see the observing software that we would normally use. Roy's kindly put this up for us all to look at. It's a little bit small, but is there a wind speed monitor there? Yeah. Yeah, so it's like 20 meters per second right now, looks like. So about, what is that, about 40 miles an hour, something like that?
Yeah, the weather page showed like 48 or something, so yeah, that matches.
Yeah,
You can
so
see
this is, oh, go ahead, Roy.
I think you can see, just move my arrow. That red line is the limit, and we're up here at this blue line. So the wind has to be slower than this for them to be able to be even willing to open. And we're at triple that. Bad.
Yeah, and looks like temperature outside is -3 degrees C, so something like 25 degrees Fahrenheit. Humidity is actually okay, so relative humidity, it looks like it's about 25%, so we're 1 for 3, I guess. But that doesn't count for astronomy, so you got to be 3 for 3.
So I don't know, Brian, if we want to talk about these observing windows or do a little science background. I have some slides I took from one of my classes on galaxies for a little bit of background on galaxies, which I can go over. Or if people would like to hear then we can talk about what our science was going to be. Maybe you can do that, Brian. And
yeah, let's go over like a little bit of science primer. That'd be great.
Okay, so let's take a look at some pictures of galaxies. Get this to come to the front. There we go. All right, so our research group is looking at galaxies, and we're actually going to be looking at very far away galaxies. So the light from those takes a very long time to reach us. So we're looking at them the way they were a long time ago. And Brian will tell us a little bit more about that. But I thought a little primer on galaxies wouldn't hurt. So galaxies are composed of stars and gas and dust, but primarily we think of them as composed of stars, and from hundreds of thousands to hundreds of billions of stars, depending on the size of the galaxy. And many of you might be familiar with this picture here, which is the Hubble Deep Field, which is a teeny tiny portion of the sky that's the size of one of the small craters on the moon, if you looked up at the moon. And almost every little dot in this picture, let me see if I can make it even bigger, is a galaxy. And some of them, you can see their colors of blue spiral galaxies, like this one and this one, unusual red spirals. There happens to be a star. But almost every dot is a galaxy filled with stars. And some of them are very far away and some of them are closer by. So what we'd like to know is how galaxies get their shapes and how those shapes and colors and the content of the stars changes over time. So when we look at galaxies, we generally classify them into different shapes, and Edwin Hubble, after whom the Hubble Space Telescope is named, created this classification scheme, which we call the Hubble tuning fork diagram, because it looks like the kind of tuning fork that you use to tune your piano or violin or whatever. And you see the spiral galaxies, of which the Milky Way is one of them. So they were classifying galaxies based on their shapes. And some galaxies have bars, and spirals have bars in the middle. The Milky Way does actually, and some don't. And then usually the pretty pictures you see of galaxies are always spirals because they look interesting and have lots of structure. But there's a lot of these elliptical galaxies out there in the universe. And the reason you don't see lots of pictures of them is because they're boring. They're kind of ellipses, kind of ovals, reddish shaped, and you don't see much structure. And so there's only so many pictures of these that you can look at before they all look the same to you. So, but there's lots of them. And we also see that the different types of galaxies in the nearby universe live in different places. We see lots of these elliptical galaxies where galaxies are close together, and more spiral galaxies where galaxies are not so packed together. So we'll talk about that in a few slides. And one of the things we want to understand is, why is that? Why is it when galaxies are close together, they look like this, and far apart, they look like this? And we're not just looking at the shapes, we're looking at the colors. The bright blue galaxies, the spirals, have young, hot stars in them. Those stars glow very bright. They're blue, but they only live tens to hundreds of millions of years, and then they die out unless you keep making new ones. These galaxies aren't red. Those are cooler, older stars, and there's no young, hot stars in these. They're not making stars anymore. So not only do these galaxies look different in color and shape, we can actually tell that these galaxies, the ellipticals, made their stars a long time ago and aren't making any more stars. And in most cases, don't even have any gas left to make more stars. So they're geriatric galaxies. And these spiral galaxies are like teenagers or little kids or something with still a lot of energy to go. That's our parents talking. And when we look at where galaxies are in the universe, we see that most galaxies do not live all by themselves, much like people. Instead, they're distributed either in small groups like towns, or in big giant piles of galaxies that we call clusters. And here's an example of a group. And here's a very rich cluster. And you can already see that this rich cluster is full of these red galaxies, but the group has spirals in it. So I often say this is like looking at the cities and the towns, and then there's like rural areas, and there's transition areas between them, like the suburbs. And so what we're doing in our research is doing sociology of galaxies. Why do red galaxies like to live here? What makes them red? Were they born red in these places where there's a lot of stuff, or did they become red as they moved in there? Why are these spiral galaxies in this kind of place? And that's what we're trying to figure out. The other thing we can see is that not only are galaxies, and actually I should say this is true today, but as we look further back in time, we can see the beginnings of these clusters as cities are growing, and they're not as filled with ellipticals. And this picture shows sort of what galaxies look like as we go back in time, where this is the early universe, the age of the universe only 2 billion years ago, to today when the universe is almost 14 billion years old. And you can see that galaxies get bigger, they get more massive, they build up their stars and their mass, but with time. So they start out small and irregular, and then they somehow become these more normal shaped galaxies, or what we think of as normal. We're trying to understand how this changes with time, why these galaxies change with time, and why these changes are different in clusters, groups, and in what we call the field, where galaxies kind of live by themselves. And one way to think about this is to think about what happens in the universe as a whole. The early universe, the material is distributed relatively smoothly, relatively evenly, with tiny density fluctuations. And the areas that are teeny bit more dense, the gravity is a little bit more there, so it pulls stuff together. And then clusters and galaxies tend to form in those areas. And then the distribution of material in the universe today looks like this. And what we're doing with our research is we know what galaxies look like today and how they're distributed. And we're looking back in time. And I'd say we're somewhere in between this first box and this second box, maybe kind of close to the second box, in where we're looking back in time today with our work. And I think I'll stop there for just a little bit of a quick background, and we can talk about things that might change galaxies over time a little bit more, and people can ask us some questions. Or if Brian wants to take over. This is a quick background of the kind of idea we're looking at.
So if anybody has any questions, feel free to put them in the chat or raise your hand. And it looks like Celestine has a question about what causes the galaxies to become compressed. So basically, I guess to change shape, spiral versus elliptical, maybe. You want to answer that, Roy?
The answer is a lot of things. So, and that's actually one of the questions we're trying to answer is which physical processes, what are the things that happen to galaxies that are most important in different places? So I like to do this when I talk to people, and Ekta and Brian have heard this 1,000 times, so sorry. But I like to think about like how people change when they move from like the suburbs to the city, or from, rural areas to towns to cities. our personalities change, our political views change, our diet changes, our habits change. And the question is that because there's more people close together in cities? Is it because you meet more different kinds of people? Is it because you actually physically bump into people on the street more often? Is it because the TV stations are different? And all of those are important. And one might be more important in a big city and one might be more important in a suburb. And so what we're trying to understand is actually which of these physical things that happen to galaxies that are similar actually cause these changes. Some of it.
Roy, I'll add one thing to that analogy, which I think is a great analogy, and I use it a lot too. And I do think of it, what we're doing is kind of psychology of galaxies in some sense, but also certain types of people may consider moving to the city or moving to rural areas versus other types of people. And so that there's some selection bias associated with who ends up in a city versus who ends up not in a city. And so the same thing is true with galaxies. Galaxies being born in certain places or having certain characteristics, because they have those characteristics, it may be that they're preferentially associated with some environment. So that could be red galaxies, as Roy mentioned, red galaxies being preferentially associated with high density environments, or blue galaxies preferentially associated with lower density environments, or a plethora of other properties. And so, yeah, there's some predisposition there with people and also with galaxies, that when you observe a set of people or do a study, same thing with galaxies, you have to take that predisposition as best as you can. You have to take that into account.
And here's just one example. This is a computer simulation of taking two galaxies that look like the Milky Way. It could be like Milky Way and Andromeda. And if they come together from their gravity, which is actually what will happen to the Milky Way and Andromeda in about 3 billion years, then they rearrange themselves. The material gets rearranged. The collision, the stars don't collide with each other, but their orbits do change. But the gas that's in those galaxies actually kind of sloshes together. And when that happens, they start making more stars because the gas gets compressed. And so the gas gets used up, and eventually there's no gas left to make young stars. And so what you see is, if you collide two galaxies, two spiral galaxies, you can make something that looks more like an elliptical galaxy. But we also know that there's not enough spiral galaxy collisions to make all elliptical galaxies. So this cannot be the only thing that happens. And we also see in the early universe that lots of galaxies don't look like spirals. They look like irregular or mishmashes of stuff. So this is just an example, and this kind of process is not likely to happen in the biggest cities in the clusters, because the galaxies are moving so fast that they zip by each other and actually can't catch each other gravitationally. But in smaller towns, this can happen. So maybe galaxies merge and turn into ellipticals in a smaller town, and then eventually move into, or fall, that whole town falls into a big city, the kind of way our cities are growing and eating up the suburbs around them, and people are like moving from the outskirts into the suburbs, and that's all getting subsumed into cities. So all these things could be happening. So there's no one answer. And the physics of this is all sufficiently complicated that we can't quite put the recipe into a computer and model it. So in some ways, what we're doing is taking data that helps people who make simulations figure out what they need to put in their simulations, like which spices they need to put into their recipe and how much which physics they need to put in to make things work and look like reality. They can make simulations that make galaxies look like the way they do today. But then if you look at those simulations from 10 years ago, they didn't make galaxies that look right 10 billion years ago. When we observe those faraway galaxies, they don't look the same way in real life as they do in those simulations. So the way that they cook the galaxies isn't right.
Yeah, so there was another question that was related to that by Sanvi, that asked about our Milky Way being a spiral. So the fact that the Milky Way is a spiral, does that necessarily mean it's a relatively young galaxy? Which is an excellent question. And I can take a shot at this. So no, it does not mean that. The Milky Way is at least the oldest stars in the Milky Way are essentially the age of the universe. So in the globular clusters that are big conglomerations of stars that orbit the Milky Way, and in the disk of the Milky Way, there are stars that are essentially, it's a little bit difficult to age date, but essentially consistent with the age of the universe. So these are, some of the first stars that formed in the universe, and they happen to be housed in our Milky Way. But that's true of most galaxies. So there are certainly subcomponents of the Milky Way that are very old, but many of the stars in the galaxy, in our galaxy, have been born within the last 10 billion years. So about the last 75% of the history of the universe. But I think the heart of the question is, so spiral galaxies, if the kind of evolutionary cycle of spiral galaxies is, you form in these kind of irregular shapes that Roy was mentioning and showed in one of the slides there. So in the very early universe, you have these kind of knotted, really irregularly shaped galaxies. They don't look like they have a lot of coherent motion like a spiral galaxy does. So spiral galaxy can almost be thought of as like a solid body rotation. It's not exactly that, but something like that. So like a top spinning. These irregular galaxies, they over on the left here in this slide, all sorts of knots of star formation, very chaotic, a lot of pressure coming out from young stars, blowouts, all these kind of galactic winds of gas and dust. And then eventually things settle into this spiral shape, and then something happens potentially, and then they become ellipticals. And so if the Milky Way is not young, then how would it not be an elliptical at this point? But as Roy mentioned, there are a lot of processes which can cause a spiral galaxy to change into an elliptical. And the physical processes are sufficiently complex that if you have a single galaxy, you can't necessarily say by that shape that determines how old that galaxy is. So this is why samples of galaxies, you can say, okay, well, spiral galaxies on average are probably younger. So the stars in them, so if you add up all the stars and you kind of, you say, okay, let me take all the light from all the stars and let me determine how old that light is. In spiral galaxies, you'll generally see that you get a younger age than in elliptical galaxies. Elliptical galaxies are, most of the stars are consistent with the age of the universe, or something close to that. But in the Milky Way, you'd see something like, 5 billion years old or 3 billion years old, something much more recent. So what it does mean is that if the Milky Way has some stars which are old, some stars which are new, but it's still a spiral galaxy, probably the processes that Roy mentioned, like these major merging processes, two galaxies coming together that are about the same mass, same size, and interacting with one another, that probably hasn't happened in the history of the Milky Way. It may be that smaller galaxies have coalesced, and we in fact have evidence that smaller galaxies have coalesced, fallen in, subsumed into the Milky Way, but these haven't been big enough to meaningfully transform the structure of the galaxy in terms of spiral versus elliptical. But as Roy also mentioned, in 3 billion years, Andromeda and the Milky Way are going to merge with one another, or at least start to interact with one another. Andromeda is actually more massive than the Milky Way, and so the two of them coming together are likely to form an elliptical galaxy. So 4 billion years in the future, because that timescale is probably 1 billion years or 2 billion years, 4 to 5 billion years in the future, the Milky Way will in fact be an elliptical galaxy, potentially. So it's complicated. So I can go over a little bit of what we, oh, thanks, Roy. Yeah, nice. So Roy's showing here, not a picture of the Milky Way, I don't think. Is this a picture of the Milky Way, Roy?
We can't make a picture since we can't fly out of the Milky Way. So no, but one of the interesting things I want to point out is, like as Brian was saying, if you look at the center of the Milky Way, it's reddish, and there's dust that makes it that way, but it's actually got old stars in it. So the center of the Milky Way kind of looks like a little elliptical galaxy. But it still has gas, so it just hasn't used it all up. So it can make stars. And those young hot stars are incredibly bright. One of those super bright young hot stars, which are also very massive, they're about 50 times the mass of the sun. They're also about 1 million times as bright as the sun. So you don't need a lot of those blue stars to make the galaxy look blue.
Yep. Yeah, so those are actually so the galaxies that we were planning on looking at tonight, in the last couple nights, probably don't fall into either of these categories, in fact. So probably not elliptical galaxies, probably not spiral galaxies. The galaxies that we're looking at are kind of just to the left of that dashed line there in that figure that Roy's showing on his screen. And so there are going to be much more of these, young, irregular, highly star-forming, knotty, very dynamic galaxies. So they're galaxies that have basically, they haven't settled their personality yet. So they're kind of trying to figure it out. They're going through their adolescence. They're trying to figure out how to, I don't want to personify them too much, but they're trying to figure out how to balance the pressure that comes from radiation pressure of the stars, young stars going supernova, so blowing up and expelling a bunch of kinetic energy into the galaxy. Their black holes are starting to grow at this age. So most every galaxy has a black hole in the center. As Roy mentioned, there is gas in the center of galaxies, so that gas can coalesce into the black hole. It can fall into the black hole, and as kind of a death rattle of that gas, it expels a lot of energy. So very high energy light, and that creates pressure for the surrounding gas, and its own gravity. So trying to balance these two things, a lot of astronomy is balancing pressure and gravity. And so, spirals and ellipticals, they kind of have this figured out after, 10 billion years of evolution. But the galaxies that we were planning on looking at and that we generally look at are these much more irregular types of galaxies. So they're harder to classify. But there's lots of different kinds of classification in astronomy. So basically what astronomers do is they take images, or they take very specialized observations called spectroscopic observations. That's not what we're taking tonight, but we take images in different colors. So we could take an image in red and an image in blue, and we could contrast that. Spectroscopy is a way of measuring the amount of intensity of light at every single color. So it's basically like taking a bunch of pictures, 1,000 pictures all at once, but of single galaxies or maybe hundreds of galaxies, as opposed to pictures, which can look at thousands or tens of thousands of galaxies in the same amount of time. So what we were planning on looking at tonight is basically classifying galaxies in terms of their color. So it's nothing really much more complicated than that. And for anybody that did the pre-activity, we talked a little bit about how different images can look different in different colors. And so if you put on rose tinted glasses versus polarized glasses versus no glasses versus blue glasses, you'll see an image in a much different way. So we had one example here of 4 images at the same time. The top left being just natural seeing, so you just look at it with your eyes, and then the other 3 panels being different color filters or sunglasses. And that's basically what we're doing with the telescope, or what we were planning on doing with the telescope. So you can take an image with no filter, that's possible, and then you just get all the light from all the different wavelengths, so all the different colors. So a wavelength of light is a certain kind of color, so we quantify it in astronomy. So we say, okay, that wavelength is 1,000 nanometers, and so that corresponds to some color, but we don't think about it as colors. It's just that quantifiable unit. So 1,000 nanometers, that's red. And so we take a picture in the red, and then we look at a picture in even further red, so far infrared, let's say 1200 nanometers, and we say, okay, are these galaxies brighter or less bright in that redder color? And by making that classification, we can actually, so if Roy goes back to the picture of the spiral galaxies versus the elliptical galaxies, you can tell just by looking at them that they have very different colors. And so even if you didn't know the shape of so even if we didn't have these exquisite pictures where a lot of these are probably taken from Hubble or they're nearby galaxies, where you don't have the kind of resolution that you can actually pick out the galactic structure, you can still say, oh, okay, that one's red, that one's blue, and that means something. That means something about how many stars they're forming. That means something probably about the shapes, and spirals are usually blue, ellipticals are usually red. In the very early universe, since most things are irregular galaxies, blue versus red in our observations actually is specifically used to tell how many stars are being formed in a given galaxy. So we were planning on using an instrument called MOIRCS on Subaru, on the Subaru 8.2 meter telescope. And we do have time again later this month. Hopefully the wind has died down by that point. And we will have a Shadow the Scientist session, hopefully with real observing, on the 29th and 30th of March. And we actually have the Keck-1 telescope, which is a 10 meter telescope right next door on those nights as well, where we're going to be taking spectroscopy. So it should be pretty exciting, but for now, we're just going to have to imagine. So with this MOIRCS instrument, we would take a picture just in a single color, actually. So we're targeting a suspected group or association of galaxies, a forming cluster of galaxies, so one of these forming cities, at about somewhere between 1 and 2 billion years after the Big Bang. I hope I'm right on that math, something like that. So let's say 2 billion years. What's a half a billion years between friends? So 2 billion years after the Big Bang. And so if we take a picture in a certain color, we have pictures already that have been taken from another telescope in a color that's kind of blue of that color. And we contrast these two images. So we say, okay, this object appears to be blue, with these two pictures. This object appears to be red with these two pictures. And so we can immediately tell how far away that object is and how many stars are being formed by that object, by that galaxy. And so our idea is to we actually don't know, because if you remember the cube that Roy was showing earlier of the kind of evolution of the gas in the universe, of the dark matter in the universe. Yeah, this one. So you can see as you move backwards in time, so we're looking further away, which is backwards in time since light has a finite speed. You can see that the matter density that is somewhat obvious. You can pick it out where the dense regions are and the less dense regions are on the right. In the present day, it's very, very hard to tell that when you go all the way to the left. The matter distribution is much more uniform. And so it's actually extremely hard to pick out associations of galaxies at these distances. It's much more diffuse. The density contrast is much less. So we're trying to determine, okay, is there actually something there or not? We don't know. And so if we discover something that's there, then the question is, what are the properties of the galaxies that are falling in to these newly forming cities? Are they galaxies that are really highly star forming? Are they, because they're interacting with other galaxies and start bumping into each other, does that do something to them as they fall in? Or are they kind of the same as the galaxies that are sitting in isolation? And we can start to get at, if we look at these different types of structures at different times in the universe, we can start to pick out what is nature and what is nurture. So what is we can start to map out kind of an evolutionary scenario and say, oh, those galaxies that were doing this at this time, now they're doing this at this next time, and now they're doing this at this next time. And we statistically connect, it's not the same system, but we statistically connect all these different systems to draw a picture of how galaxies evolve as they fall into these types of systems. So that's what we were planning on doing. But unfortunately, we couldn't tonight. But we've taken a lot of other observations like this, and we've actually found some reasonably cool things with it. Maybe Ekta, do you want to talk about a little bit about like LATIS, if you're familiar enough with it, like kind of what the concept was of this particular proposal, or maybe just in general, like, you know, kind of what we're doing with the narrowband observations?
Before that, actually, I wanted to talk about like protoclusters and what we do.
Yeah, it'd be awesome. Yeah, anything.
Just 1 second. Here, okay, let me share my screen. I cannot, since Roy is sharing, I cannot, yeah. So, as Brian said, we have already taken lots of observations, and so using those observations, I wanted to just give idea about what kind of science we actually do. So here, sorry, I need to remove the chat. So this is just an example. So once we have actually information about different galaxies, one of the things that we do in our group is we construct a density map. So basically we are trying to get idea about where do most galaxies lie in kind of cluster environment. So sorry if this is a bit overwhelming, but basically the colors that show where do most galaxies are. So redder the color, higher the number of galaxies in that region. So doing something like this gives us rough idea about the kind of density distribution of cluster. And based on this, so you can kind of see somewhat the morphology or the shape of the cluster and how many very dense regions are there. And of course, at different times of the universe, these kind of clusters look very different, and different clusters even at the same age of the universe can look very different. So what we kind of do is you can ask, like, so there are galaxies, there are lots of galaxies in the redder region, and there are less galaxies in the kind of bluer region. So now you can ask lots of questions about the properties of galaxies and how this kind of dense environment affect the properties of galaxies. So for example, since there are lots of galaxies in this kind of dense environment, you can ask, like, how does this dense environment affect, let's say, the star formation of galaxies, the shape of galaxies? And when you look at them, you see that these properties of this dense environment galaxies are very different compared to the properties of like galaxies that are kind of hanging out by themselves. So kind of galaxy village versus like galaxy cities that Roy was mentioning earlier. So in our group, that's kind of what we study. And along with like the star formation rate of galaxies, as Roy had showed, like galaxies that are going through mergers. So since there are lots of galaxies in this kind of dense environment, and you have to think this as kind of dynamical system. So over time, things are changing. So in this kind of dense environment, there will be lots of mergers of galaxies that will be happening compared to when galaxies are in isolated state. And when they go through merger, as we discussed earlier, that can also affect the shape of galaxies, star formation of galaxies. So we also study that at different stages of this kind of formation of this cluster, how did this merger take place? How frequent was the mergers in this dense regions, and how that affected the properties of galaxies. And along with star formation, there are also black holes in most of the massive galaxies. So how does the black hole activity of this massive galaxies get affected in this dense environments compared to the isolated galaxies, and also in different parts of the protocluster. Like if you look at the outer part of the cluster versus like the central region where lots of other things are happening, how do the properties vary? So there are lots and lots of interesting questions you can ask. And our group has great data spanning like huge range of the age of the universe. So almost like starting from now. So there are lots of data available in the nearby universe, and our group has great data in the early universe. So from that, we can kind of get sense of like, if you look at very early universe, when this protoclusters was just forming, the role of this dense environment were very different compared to right now. I'm trying to decide how much depth I should go to. So in the early universe, when these things were just forming, there was lots of gas available in the universe. So this dense environment, it looks like they were kind of increasing star formation rate a little bit compared to right now, where there isn't a lot of gas available. So now what happens is, if you are in dense environment, the gas kind of gets ripped off from the galaxies. And now this dense environment, if you look at like galaxy clusters, they have lots of elliptical galaxies that Roy showed earlier, which means that gas is kind of ripped off when the galaxies are going through this dense environment, and that results into kind of lowering of star formation rate or stopping of star formation rate in these galaxies. So the role of environment varies a lot throughout the evolution of the universe. And having this kind of great data, we can kind of build a coherent picture of exactly how these dense structures are forming, and how does the dense environment affect the properties of galaxies, and what can we say about the role of different processes that play in the evolution of galaxies. So yeah. Any questions so far? No.
Yeah, Ekta, I'll just add to that, that in the picture that you just showed, the reconstruction that you just showed,
yeah.
So first of all, that's not a simulation, that's real data, which is amazing. But one of the things that's really important actually for what we're doing tonight, or again, what we were planning on doing tonight, is what you're showing there is galaxy density, right? So on the color bar there, it's weird, like it's hard to tell exactly what that means, but you see gal as part of that, right? And that's not referring to the density of Roys, but rather the density of galaxies in the early universe. And the structures that we were targeting tonight, that were part of this proposal, and that we're going to target later this month, actually don't seem to have a whole lot of galaxies in them. So if galaxies are the people that populate the cities, we're looking at cities that seem to be devoid of people. And the question is, what happened? Where did all the people go? Because unlike the city people analogy breaks down in that, these clusters, these cities, they're made of, in part, the galaxies that are there. So at least a lot of the gas and dust that eventually ends up in a cluster environment comes from the galaxies that have coalesced into that environment. So those galaxies have been stripped of their gas and dust, and it's been deposited into the overarching cluster environment. However, the structures that we were targeting tonight, they don't seem to have galaxies in them. So we can tell that there's a lot of matter there. There's infrastructure there. There's things like houses are built, the rec center is there, everything's there. They got the stadium going, but nobody's coming to the games. And so what's going on? Is that something having to do with that particular city? Or are there different types of people that live there that we don't really understand or don't know anything about? We can't see them with our optical observations, our near-infrared observations. Maybe they're radio people, so we have to look in the radio in order to be able to see them. And so maybe you could talk a little bit about that, like why we're taking the observations that we're planning on taking tonight.
Yeah. So yeah, I was going to come to that. So basically, as Brian said, that based on certain observations, we do see properties of cluster, right? So we do see properties of cities, as Brian said, we see like structures build up and all. But based on the city analogy, we know that structures are built by people. So but if we don't see people, what does that mean, right? So similarly, we have based on certain observations, we see there is hot gas available. So these are kind of properties of galaxy clusters. But using some optical data that we usually use to see like how many galaxies are there, there don't seem to be a lot of galaxies in the region. So here, as you can see, I'm trying to annotate. But okay. That is, okay, I can't annotate right now. So, but basically, where it says the lattice structures, the big circles that you see that Brian is highlighting. So you can see that I believe the crosses here are the spectroscopic members. So so there aren't a lot of galaxies in that region, even though you do see cluster properties. So what we are trying to do here is we are targeting, based on this observations, we say that there should be galaxies exactly with this kind of colors, if there are galaxies there. So instead of like using general broad observations saying that galaxies are somewhere over in that region, we are saying that since there are clusters there, we are using the exact color filter to see whether or not galaxies are in that particular space, in that particular location, but in the Z direction.
Ekta, I'll just mention, like, so that Jamika asked about how the reconstruction was done, and we should maybe mention that this picture here is done in the same way as the other picture that you were showing. It's just not 3D. So we've collapsed it over the third dimension, which is the dimension that Ekta just mentioned. So there's the two transverse dimensions on the sky. So it's like this way and this way, up and down, left and right. But then there's also everything we see, like all this, like let's say the stars in Orion, like in the belt of Orion, for example, those stars are actually quite far away from each other along the line of sight, but they're projected in such a way that we see them in a nice line and it looks like something meaningful to us, right? So it's collapsed 3 dimensions into 2 dimensions when we look up at the plane of the sky. And so we're doing the same thing here, is we're taking the galaxies that we think are within a kind of slice of the universe along the line of sight, and we're just collapsing it into a 2-dimensional pancake thing. And we're saying, okay, where are the galaxies? It's just like looking up at the night sky and saying, oh, there's a bunch of stars over there. There's not so many stars over there. Same sort of thing, but you're limited by your eyesight, right? Like, so, you see stars because they're bright, and you don't see not bright stars because they're not bright. So same thing goes here. We see certain types of galaxies because they shine in the light that we are observing in, but maybe we don't see them because they're too faint in that particular light, or they mostly shine in a different type of light. And so we're looking in a particular type of light. And so the 2 things that are labeled lattice 2 and blah, 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 and lattice 1, blah, blah, blah. These are structures that have been determined to contain a lot of matter using a different technique than actually just counting the number of galaxies. So you can see on this map here that in those locations, we don't see a lot of red, right? There's not a lot of, and that's not the color of the galaxy or anything like that. That just says there's not that many galaxies there. So more galaxies is redder in this picture, less galaxies is bluer in this picture. We just use that as a representation. And you can see in these regions, they don't seem to be super special in terms of the number of galaxies. There's, patches of red here, here, here. These are part of the Hyperion structure that Ekta just mentioned. So these are actually galaxy overdensities, and they correspond to forming clusters. But these should also have basically the same amount of matter, we think, is in these locations, but they don't seem to have galaxies. And so why do these things have galaxies and these things don't seem to have galaxies, in at least in the observations that we've taken so far? Yeah, so I just want to mention that this is the same type of mapping that we do, and we do that, and we use both images of the sky, and we use this technique of spectroscopy, which is very powerful to tell us how distant a particular galaxy is. And so what we're doing with these Subaru observations, if we are able to do them later this month, and what we've done in the past, is to look for, it's kind of a poor way of doing spectroscopy, right? So it's looking for a certain type of emission of a certain type of element. I'm forgetting what we're looking at the emission of hydrogen and doubly ionized oxygen in this case. And these are very prominent features in a galaxy spectrum. So any galaxy that's forming stars, you'll usually see quite a bit of emission from hydrogen, which is the most abundant element in the universe, and oxygen, which is also a very abundant element in the universe. And so by taking these pictures in these two different bands, these two different colors, we're actually able to see if there's hydrogen emission and oxygen emission precisely at the distance to these galaxies. So if we see an excess of emissions, they look brighter in the images that we take relative to the images that we have from a previous telescope. We say, aha, that's the specialized emission. That maybe is a signature, probably is a signature of a galaxy that's sitting precisely at this distance away. And beyond that, we can say, okay, because the strength of that emission is some amount of units, 10, let's say, then we can translate that into the number of stars being formed per year. So it's very powerful because we take an image of the entire part of this sky, and we can just pick out, there's 15 galaxies that look to be bright in this image relative to the other image that we have. Those are probably at that same distance. Great, and here's their properties. And why this is different than what we've seen before. So the maps that we make previously are based off of ultraviolet light. So we take observations a lot of times with optical instruments. Because the universe is expanding, that's actually when the galaxy emits it, it's ultraviolet that has been Doppler shifted. So it's lost energy as it's come to us, and it's gone into the optical so that we can see it. So here we're looking in the near infrared, which was actually the optical as emitted by the galaxy. And so emission in the optical is much, how to say this? There's much less, many fewer processes which can stop emission from the optical as it traverses the universe. So as it's emitted from the galaxy, so like, ultraviolet light is emitted by very young stars, for example. So why you see blue colors for young stars is their actual peak of their emission is in the ultraviolet. So that just looks blue because running from red to blue in the optical, it's much brighter in blue, but it's actually much brighter in the ultraviolet than blue. So let's say this light is emitted from young stars. Dust, there's lots of other things. Gas can prevent ultraviolet emission from reaching us. So it can stop ultraviolet emission fairly easily. But optical emission, that gas and that dust is less effective. So it's harder for that gas and dust that are sitting in the galaxy or around the galaxy to be stopped or to stop optical light. So this is why we think potentially these observations will be better, because most galaxies actually shine in the optical that we can see. Ultraviolet, it can be very difficult to pick these galaxies out. So it may be actually just the way that we're looking at these galaxies that's making us not see them. Hopefully that was understandable.
I'll just add that whatever we find, if we find that these galaxies are there and we just couldn't see them before, that tells us that when we're making a census of galaxies in the early universe, we can't do it the way you can't just do it one way and expect that you're going to find everything. We already know that to some extent, but if a lot of these galaxies are missing just because we haven't looked at the right wavelengths, then obviously it's like doing a census of people in the city, and if you never look behind the locked doors, then you miss a bunch of people. So you have to understand where you need to look or how you need to look. On the flip side, if we find that even when we're looking the way we're trying to look now, there's still nothing, then it becomes really puzzling, because there's almost no way the galaxies could have escaped our attention in the many different ways we've tried to find them. And in that case, we've identified what seem to be giant piles of matter in the universe. Like Brian said, the infrastructure for cities that somehow got there, but the people have not populated them yet. That's pretty strange. But that means also when we compare to models of the universe, having looked in the past for galaxies as the indicators of these clusters, humans as indicators for cities, we've missed a bunch of cities because they turn out to exist without people in them.
Right, and so when we're trying to draw these evolutionary scenarios, basically trying to draw a picture of how galaxies and these structures evolve all the way from the beginning of the universe, or a billion years after the universe is formed, to the present day, if we're missing a particular type of galaxy or particular type of structure, our whole premise fails. So the census is no good, or it has inherent biases which contaminate our picture of these things, and this is really important to correct for. At least understand the things you don't know. That's really important. So if we get this idea of like, oh, okay, maybe there are these types of systems that don't have as many galaxies as we think, or maybe they're a little bit different, and the galaxies are a little bit different, and that may have something to do with how those cities or structures are formed. Then we can start to tweak our models, our understanding. As observers, we can do that with we have this census, and then we make statistical corrections to that census. And that's no different than what people do in politics or in medical studies. You can make weighting factors, you can add in probability functions, you can do all sorts of things that allow you to kind of correct for these biases, but only if you know them. If you don't know them, then you're in bad shape. And so doing these kind of explorations is really important, because we can figure out we can get hints at some of the things that we don't know. And so, yeah, I like never being confident in what I'm doing. and then trying to push things. But it's exactly through these types of observations that you can do that.
We're trying to go from unknown unknowns to known unknowns. And this is a sort of general lesson we have in astronomy. We started out looking with our human eyes that are adapted to see light that comes from the sun. And as we developed tools to see colors that we're not sensitive to, we discovered all kinds of things that we never knew were there because we can't see them with our eyes. And then we could see infrared light, some kinds of ultraviolet light, but we have to go above Earth's atmosphere to see X-rays and gamma rays and a lot of ultraviolet light and a lot of mid and far infrared light. So until we developed space technology to go above Earth's atmosphere, we were still missing a lot of what's in the universe. And so our ability to develop technology that sees outside of what our humanity can see has opened up the universe to like, oh, there's a whole bunch of other stuff out there that we couldn't see. A great example of that is the first X-ray satellites were sent up not for astronomy, but to do verification of nuclear tests. So they were looking at Earth because if you blow up a nuclear bomb in a nuclear test, it gives off X-rays. And so like the US put up satellites to look for blasts of X-rays that, like, if the Russians were doing nuclear tests, and they sent the satellite up and they turned it on, and there were blasts of X-rays from everywhere. And it turned out they were coming from space. There were things emitting X-rays, turning on and off in X-rays, coming from space. And so they went, uh-oh, now we need to understand what's coming from space so we can figure out what's going from the ground. And so X-ray astronomy was born. And we learn all kinds of things from X-rays in space now, but we could never do it from the ground because X-rays from space don't make it through Earth's atmosphere. So science, this is a kind of, our project here is a little microcosm of how science tries to go beyond our human experience and open windows to the universe that we can reach with technology, but not with our own personal senses.
Yeah, and I'll just add to that, Roy. Like an example that I experienced that was pretty transformative during my PhD thesis at Davis was looking at post-starburst galaxies. So these are galaxies that have they're preferentially seen in overdense environments like clusters. They're galaxies which have recently undergone a very strong star formation event for some reason. And then for some reason, they've stopped that star formation abruptly. So something really transformative has happened to these galaxies. So they're a very special type of galaxy, and you can really age date to pretty high precision when that star formation event stopped. And you can then say, oh, okay, that might be because that galaxy ran into that other galaxy, or because that galaxy got stripped of its gas from falling into the cluster or something like that. And so, you know, they're galaxies which are very popular to study because of these properties. And everybody was, you know, studying them, and they were studying them using certain diagnostics, usually looking at optical data. So basically, I see some spectral signature that tells me, yes, that's a galaxy which has undergone some process like this. So I make a classification based on a certain wavelength of light, and I say, yes, okay, good, that's that type of galaxy. We can move on, and, you know, we can talk about physical processes which cause the quenching of star formation. Well, then a mid-infrared satellite came out, and that mid-infrared satellite called Spitzer started taking pictures of these galaxies, and everything changed. About some fraction of these galaxies were actually galaxies that were kind of on their way to dying, that they'd quenched their star formation, they'd stopped star formation, something had abruptly truncated their star formation, and they were what we thought they were. Another significant fraction of that population were galaxies that were emitting very strongly in this mid-infrared, which indicates that there's a ton of dust in those systems coming from dead stars, basically, but that there's a lot of ongoing star formation in these systems that's just being blocked by that dust. So I said earlier that ultraviolet light from young stars can be blocked by dust surrounding them. It actually gets reprocessed into mid-infrared light. So all of that blue light transforms into really red light, and we couldn't see that from the ground. As Roy said, certain wavelengths we have to go to space to be able to see. And so these were galaxies which were in fact the most highly star-forming galaxies in these cluster environments, and we had wrongly classified them based on the light that we were looking at before as being basically devoid of star formation activity. So they were the exact opposite of what we thought they were. And we were all confident, we were, you know, doing our models and all this kind of stuff. Then you go to a different wavelength of light and your whole entire picture changes. So these galaxies are now in a completely different evolutionary stage than what you thought they were before. And I thought that was, I mean, that's amazing because you do this, you know, highly, you know, organized, what you think is very precise analysis based on the things that you think you know from the data that you have. And then you just change perspective a little bit. You just look at it from a different light, and all of a sudden everything changes. And so that's kind of what we're trying to do with these observations, or what we're planning on doing with these observations. Yeah, exactly. Yeah, so I said high precision is a relative term in astronomy, and yeah, a few 100 million years between friends. That's precise.
Brian, can I share something real quick?
Yeah, of course. Yeah.
So this is just to highlight what we were talking about what we can see from Earth and what not. So this top diagram says what fraction of the light is blocked at different wavelengths. And you can see at short wavelengths, ultraviolet, X-ray, 100% of light blocked. The atmosphere just eats it up. Here's what we can see with our human eyes when we see a rainbow. So when we think of a rainbow as containing all colors, the rainbows that we see contain a teeny tiny portion of all colors that exist. We just see the visible colors, the colors that are visible to our eyes. Then we go to longer wavelengths, which is what we would be observing around here. Some makes it through the atmosphere, some doesn't. And then Brian was talking about mid-infrared long is over here. So you got to go to space. And here's Spitzer Space Telescope, actually. And then radio waves make it to the ground. And that's actually good because we use radio waves in our cell phones to communicate. And then the longest wavelength radio waves are again blocked by the atmosphere. So all these areas are colors of light that we can't see from the ground. The universe, stuff in the universe might be giving off those colors of light. We will never see them until we go above the atmosphere. All right. That was it. Yeah, and Chelsea, what you're asking in the chat is science. We take new information and incorporate it and figure out what we knew and what we didn't know and what we're missing. And then we ask new questions. So if we, at the grandest scale, today, we understand that the material that you and me and everyone on this call and our computers are made out of is only a tiny fraction of what the universe is made out of. But 50 years ago, we didn't know that. So now we're asking, what is all this other stuff out there? We used to think that we're the normal matter, and it turns out we're the weird stuff in the universe. The stuff that we're made out of, atoms, is like 5% of the universe. If you add up all the matter and all the mass and all the energy in the universe, then the stuff we are made out of is just like the trash swept under the rug. And yet we're trying to understand what it all is. So, and we figured that out by making observations that show us things are happening that our physics doesn't explain. And then we have to explain it like, oh, there must be material there with gravity that we don't see. Now we got to figure out what that material is. Or, oh, something's making the universe expand faster and faster. There's like an energy source, but we don't know what it is. Let's go try to figure it out and figure out experiments and then incorporate that into our models. And it's just this ongoing process of learn something new, incorporate it into the model, or throw out your old model and make a new one. A really great example of that also is solar systems. 30 years ago, we knew one solar system, the one that we live in. And in our solar system, you have the sun and the Earth, you know, the small rocky planets on the inside and the big gas giants on the outside. And so all of the models that astronomers made to explain solar systems were designed to make a star in the middle with small rocky planets and then the big gas giants far away. And guess what the first solar system was that we found outside of our own? A star with a big gas giant next to it. And our models could not make those because we never tried to make them. So literally all the work that theorists, scientists, astronomers had done in trying to figure out how solar systems were made, you hear the loud sound of flushing down the toilet. Start all over. because we couldn't explain that. So that's the fun part.
I also want to add how the observations we were planning to do today are a bit different than what we usually do at, let's say, Keck telescopes, because I think some of you are were present in the earlier STS sessions when we were observing using Keck telescopes. So Brian already described this a bit, but I just want to add a bit to that. So usually what we would do is we would have this kind of image of a region in sky, and what we are trying to do is we have color information about different galaxies. So this kind of dots that you see are galaxies, and we have a rough estimate about where they could be. So what we would do is we would use a Keck telescope where we would put like slits on individual galaxies. So here is an example of one of the observing run that we had done, and you cannot see this clearly, but each of the slits is targeting like individual galaxies. So in this case, we would have like the whole thing will be black, and then we would just put slits on the individual galaxies to figure out exactly what distance they are. But remember, for this, you need to have a starting position for the galaxies, right? Like here I have a galaxy, so I will put slit on it. While in this case, what we have done today, I mean, what we were planning to do today is we have something like this. So now we have like a blank region, almost blank region, and we are trying to locate galaxies there. So we don't even have the starting point that I showed earlier, right? So the stuff that we did using Keck telescope wouldn't work here, because for that we need like a starting position of the galaxies. So now we are actually taking this kind of image itself in different colors and then trying to see the difference to see if some of these galaxies pop out in one image compared to the other. And then that will give us a rough estimate of like these galaxies are at somewhat similar distance that we expect them to be if they are in the protocluster. And then if we want to be more precise, we can target them individually once we know their position with the Keck telescope to have more precise location of them. So yeah, hope that was understandable.
Yeah, so I can share something. These are actually, well, the one on the right, so these are two different images of the part of the sky that we were going to look at tonight, in fact. So this is a field called the Cosmos field that people have been observing. It's a fairly famous field in astronomy. People have been observing it for about 2 decades now, with all different types of observations, different wavelengths of light. And it's very highly studied by a large number of astronomers. And to Roy's point in the chat, every single time we find something, because we find a lot of things looking with a lot of different telescopes, a lot of different wavelengths of light, it opens up, 15, 20 more questions to answer. So it is very much an iterative exploratory process. So the image on the right is an image taken by MOIRCS. So this is the instrument actually that we were going to use tonight. And the image on the left is taken from the Vista telescope. This is in Chile, so the Atacama Desert, High Atacama Desert in Chile. These are both same part of the sky. So the Cosmos is what's called an equatorial field. So it can be seen from both the southern hemisphere, where the Vista telescope is, and the northern hemisphere, where the Subaru telescope is. And so this observation on the left is an image taken in a broadband filter, which means that it collects about what is that? About 100 nanometers wide in light. So it's a big light bucket that collects light. Let's see, in the optical, what would 100 nanometers be? It'd be something like, let's say red.
1,000 angstroms.
Yeah, red to orange.
Yeah, red.
Just red. So different shades of red.
Yeah.
So okay, so you know, a decent portion of the optical spectrum. So like, you know, reddish orange, that kind of thing. On the right is a narrowband filter. So this is what we would be taking with MOIRCS generally, although we're using a medium band filter this time. But this will be maybe just a 10% of the wavelength coverage of the image on the left. So they're not exactly totally different colors, but we're just zooming in on a particular type of red versus this big light bucket that contains all reds. And as Ekta mentioned, so yeah, we're looking for kind of trying to pick out galaxies, pick out objects that seem to show up preferentially in this image, the right-hand image versus the left-hand image. And the scales are different. So, you know, this image, it's going to be, every object is going to be a little bit fainter just because it's harder to go to get as deep of an image when you're only collecting a 10% of the light. But when you account for that difference, that 10% that you're only collecting, you can make a difference so you basically subtract the amount of intensity that you see in this picture versus the amount of intensity that you see in this picture. And these three objects here, they're hard to see in both pictures, but I swear to you, they exist there. And they look something like the galaxies that Roy showed earlier. So they're these very irregular, weird-looking galaxies. These are all galaxies in a forming cluster that's about 500 million years further back in time than the one that we were looking at tonight. And so we've determined from spectroscopy that these galaxies are actually at this distance, and we see them preferentially shown in this picture. So this is kind of like a way of training our idea. And then there's plenty of other, so if I zoom out, there's plenty of other orange circles around that are objects that have been picked up as being brighter in this image than the kind of average object in the image. So this is how we pick things out to study in these kind of forming cluster environments. And then the difference in that intensity tells us basically how many stars are being formed in that galaxy. So this is a good example here. You can see this object is fairly intense. You can see these like white pixels, which is in this color map, that's the brightest. And these colors are not real. It's a grayscale image, but I've just assigned a certain color to bright and dim. So the white is bright and the black is dim. And then here in this picture, you can barely make out anything. So so we say, oh, okay, this object is fairly bright in this picture relative to this picture. That probably means it's at the distance of this particular system.
Hey, Brian, let me share my screen real quick. So you see that broadband versus narrowband filters image? Yep. Yeah, so that gives you an idea of what we're talking about, that in the left picture, it was like taken through, say, this pink filter. So that's through light of a lot of different colors. And then the other one was taken through just this one of these skinny filters. So let's through only those very specific colors. So if the galaxy has some kind of special emission due to some physical process that makes it give off light from, you know, ionized oxygen or something, or hydrogen, then we would pick it out here, whereas it would be kind of diluted by the broad filter. So that's what we're looking for. And if you looked at that pair of images from Brian, then that one he pointed out was bright in the right-hand image and dim in the left, but all the other ones were the other way around. Because a galaxy that, if you just have sort of equal amount of light at all colors, let's say, then the less colors you let in, the fainter the object looks. So the more colors you block out, the fainter it gets, unless you're picking out the one where it's giving off a lot of light.
Another comparison that I really like, where you can clearly see the difference between two wavelengths, this. So here on the left, you have X-ray observations, and on the right, you have optical observation. And you can right away notice that the brightest object over here on the right-hand side is actually moon, and you don't even see that in X-ray. And kind of vice versa, like the brightest objects you see here aren't even present in optical. So you can now imagine, I mean, this is for a different reason, like X-ray emission is for a different reason, but you can imagine that if you're only looking in optical, there are so many different kinds of sources that you would miss out, even if they are extremely bright in the other wavelengths. So this is also similar to what Brian had mentioned earlier about infrared galaxies that were not bright in the optical, but once you look at infrared, they are really bright and stuff. So yeah.
Just along that same vein, this is from the pre-activity, sorry, the pre-session activity that we wrote out, and this is two different images of the pillars of creation, which is a famous Hubble picture, taken in the visible, so in what we call the optical range. So this is like what humans can see, but of course it's taken with a space telescope that has a fairly large mirror, so it doesn't have to deal with the atmosphere. It's much bigger than our eyes. So it can collect light, that's billions and billions of times fainter than we can see. And so, but if we had, if we were sitting in outer space and we had 3-meter sized eyes, and we could, integrate the light for for a long period of time rather than just seeing it, second after second, this is what we would see. So this is not like false color; it's more or less real color. And you see these big lanes of gas and dust. And then a background of stars, but not too many stars. There's some really bright ones here, a few fainter ones in the background, and then you just shift by a factor of 2 in wavelength. So you just go from the visible, from the optical to the infrared, and the change is incredibly dramatic. So the gas and dust that was blocking the starlight, that's diminished quite a bit. And then you see all these lower mass stars, these redder stars, just pop out in the background. And as I mentioned earlier, so young blue stars, they actually peak in their emission in the ultraviolet, and we see them as blue because they're brighter in blue than in red. But the lower mass stars, which are the most abundant stars in the universe, these are their light is going to peak in the red or in the infrared. And so that's why, in part, that they're visible in this picture and not visible in this picture. But really, it's the gas and dust that's in this star-forming region. So these big pillars here, this is blocking the light from the stars in the background. And so, as I mentioned earlier, ultraviolet light or optical light can be attenuated, can be reprocessed, is fairly easily blocked by gas and dust, whereas if you go in the infrared or in the very red part of the optical, that same effect isn't there. And so same thing goes, like when we're looking at these structures later this month on a hopefully clear night on Maunakea with no winds, if maybe before we were looking at something like this, right, and we're like, oh, okay, there's a few stars there, like neat, that's cool, but there should be a lot more stars there. I don't understand, like, we predicted there's a lot more stars there. We know that there's a lot of mass there. So why aren't there stars there? Then you go over this picture and you're like, oh, okay. All right. So yeah, there's all the stars that we expected. That could be one way. That could be one thing that happens. or perhaps we don't see those stars, and then that's interesting as well. So yeah, it's really a matter of perspective. Yeah, that's an amazing picture, Roy. I love that picture. I have a poster of that.
Well, we've talked a lot about science. Did you want to talk any about like what it would be like to observe if we were observing?
Sure. Let's make ourselves feel better. Let's do some mock observations. Can you spin the telescope around in a circle or something?
Actually, we have no control of that, right? They don't let the astronomers control these big telescopes.
You know, actually, I started the Gen 2 software in interactive mode. I don't know if you have interactive capabilities there,
No.
but
No.
probably for the best. All right. So good thing I'm not at the base facility. I might be tempted.
Let me put up my screen then. Hold on.
How did you get access to interactive mode, Brian? I thought they only give access in terms of just like viewing, not interacting.
Wow. It was because at the base facility, you can choose your own session on their computers there. And so you can start the observing software session either on the summit, in the base facility, and several other places, either in non-interactive or interactive mode. And so this is so that the astronomers there at the base facility can actually interact with the telescope in some way. So they use that sometimes during the day to interact, do checks and stuff like that.
I see.
But yeah, so when we do the like GEARS thing, which is the thing that Roy's showing now, they don't allow interactivity. And I think that's they're worried about network, people connecting to the network and sabotaging that, and actually, controlling the telescope when they don't want people controlling the telescope. So yeah, no remote access outside of the base facility. We did the same thing at Gemini, kind of. You basically have to be either physically at the facility, or you have to have a special VPN in order to get access to any of the functions of the telescope. And in fact, there's some switches at our base facility that you have to physically go in and press in order to control the telescope from the base facility, because last thing we want is moving around the telescope when there's people around and the day crew's there, they're not expecting it, that sort of thing. So you can do like kind of internal instrument stuff. So we could probably even, like, if I was at the base facility now, we could take some biases with MOIRCS. We could just take a few pictures and stuff like that. But you don't have to move the telescope around for that, right? It's just taking images of internally in this giant instrument. But yeah, moving the telescope around would be a bad idea. So yeah, so these are the GEARS screens. These are the observing screens that we normally use to observe with Subaru. And there's a lot of them. So I think in total there's 8 desktops. So when I'm observing from the base facility at Subaru, and it's the same thing for Gemini. Yeah, we have 8 screens. Jamika, you remember the 8 screens? We mapped those all out for the Shadow of the Scientist sessions for Gemini North. And they all have like, I mean, I think the Gemini North, the one and only Gemini North session that we've done, because our mirror is damaged and we haven't been able to go back on sky for about 6 months. We basically picked all the screens. Like we like, oh, hey, there's this screen. Like, let's talk about what this screen does. There's this screen, let's talk about this. And each one has a specialized function, and it could be monitoring. So like the screen in the upper left here that Roy has, this is all monitoring displays. So it'll tell you like where you're pointing on the sky, probably something about the cable wraps. So there's cable wraps around the different parts of the telescope. And so as the telescope moves, the cables get stretched. And so you may need to unwind things. You don't want to be pulling cables out of an instrument as you're moving across the sky, because of course the telescope has to track as the sky moves. So you can keep track of things there. So these things that say like time to as limit or time to L limit, these have to do with cable wrappings or with the actual physical structure of the dome blocking the telescope. So that as stands for azimuth, that's kind of degrees east of north. And then elevation is degrees up in the sky. So 90 degrees elevation straight up and then 0 degrees elevation down the ground. But we saw a picture of the dome earlier, 45 degrees angle of the Gemini dome. It's this big structure. And it has, this shutter that we couldn't open up for Subaru. And the shutter can only dip down to a certain level. And so you have the kind of engineering constraints of the telescope, because as it points down, I mean, you have instruments that are attached to it that can weigh several tons. And so you have to have a very careful balancing of all the weights that are on the telescope. And of course, there's shear forces because of these different weights. So bringing the telescope down to a very low elevation can really push the structural integrity of the telescope. But also the dome itself will block parts of the sky because it's built in a way to optimize observations that are usually more than like 30 degrees. Our elevation limit, I think at Gemini is 18, something like that. But the dome is not built for you to go down to the horizon. And in fact, observations down at the horizon are not very helpful because you're looking through a lot of atmosphere. Things twinkle a lot more. It's just very messy down there. The photons, the light waves get attenuated. And so, yeah, so Roy's putting up a picture of the Subaru dome. This is what Subaru would look like on a normal clear day, open during the daytime, pointing directly at the sun. Super smart. So is this a real picture? Or is it just like some mock-up? It looks like a real picture.
I can't imagine being open looking at the sun.
Yeah, normally you don't do that. So maybe
this is just a beauty shot. Yeah, it's
a
photo op.
They were probably open for 2 seconds to take that shot and they closed right back down because you don't want to be pointing that thing at the sun. Even during the sunset, they pointed away from the sun to thermally equilibrate the dome. So
the mirror is down here.
Yeah, so you can see like if the telescope went down to like 90 degrees, the physical structure of the dome would actually block part of that. So there's an elevation limit, and probably it's somewhere 20, 30 degrees. Actually, Keck right now, they're having a problem with the bottom shutter because it basically opens like this. So both you have like a top shutter and a bottom shutter that open up, and they're controlled separately so that you allow the least amount of light that you don't want in. And Keck, their bottom shutter is broken right now. So we have an elevation limit that I think is like 40 degrees, something like that. And so we can track targets for longer. Yeah, that's a great picture there. So you see the top shutter is all the way open on both of them, and then you have the bottom shutter. So Keck 1 is on the left, Keck 2, these are twin telescopes, is on the right. And you have the bottom shutter open to different degrees for the two telescopes, and that depends on where the telescope is pointing. So their shutter's broken. So when we observe later this month, we either have to keep our targets above 40 degrees, that's our elevation limit, or you can still keep going, but what happens is something called vignetting. So basically you start getting part of the telescope that's blocked off by the bottom shutter. So you can still get images, but you get less light of those images. So they become dimmer and dimmer and dimmer until the point where the shutter completely blocks off your telescope and then you don't see anything anymore. So we're going to try to not do that. We'll try to keep things kosher above 40 degrees on our run. So you want to keep monitoring like all of this kind of stuff. This is really important. As we talked about in the beginning of the session, there's like wind speed monitors, there's humidity monitors. It's very, very important. I mean, one of the primary responsibilities for any observer and they actually don't leave it in our hands as guest observers, is making sure the telescope, the instruments are safe. So if there's ice flying around, if it's getting humid, every observatory has very special conditions that say, okay, if we reach this limit in wind speed or temperature or humidity, and this can even vary based on the time of year, or for example, whether volcanoes are going off in the Big Island. So we just had the Mauna Loa eruption. We've had Kilauea, which has been erupting for quite some time. And this will dump a bunch of SO2 into the atmosphere. And so this can this has a deleterious effect on the instruments and the mirror. And it can create soot on the mirror if the humidity is too high, which is very hard to clean off. And so our humidity limits actually change based on whether the volcanoes are active and how active they are. And that can be kind of sad. So you can come on an observing night and you're like, all right, looks good. It's only 50% humidity. Like, wind speed looks good. Sky looks clear. We're all ready to go. And oops, volcano went off today, like super powerful. And so, no, actually, we can't observe. We have to have less than 40% humidity. And so astronomy is always an adventure, but it's a long-term adventure. The longevity of the telescope, the instruments, that's what's important, because observing on any given night, yeah, it may seem really important to us. Oh, we have to do this. We have to publish this paper. We're super interested, but the universe has been around for a long time. Subaru for less so, but it's been around for a decent amount of time. Want to keep things moving, going, and so other observers can answer other questions. And so making sure, so there are people that are, from the observatory that monitor this and decide when to close or when to open. And so for Gemini, I can act in that role because I'm observing for other people. But for Subaru, they tell us, yes, you can open. Nope, sorry, I got to close down, and we're gonna have to wait this out. So yeah, so this is just the first kind of interface screen. So hopefully you're not paying attention to this. Everything's going well, you're good, you don't need to pay attention to it, but alarms go off, as things start to go wrong. You may have to switch targets, or one of the things that we had talked about going into this night is the wind is coming from a certain direction. And so pointing the telescope at that direction where it's face onto the wind, that can cause more wobble in the telescope. It can cause our images to blur out. It can actually be harder on the structural integrity of the telescope because the winds were so strong. And as I mentioned, it's kind of a delicate balance for all the weights that are on the telescope. And so picking targets that are actually perpendicular to the wind can be helpful. So your images can be better, and the wind speed, the level of wind speed that there can be to maintain structural integrity can be higher because you have basically the dome blocking the way. And so thinking about all this stuff is really important when you're observing. So it's not just like, oh, I want to point to that part of the sky and I'm going to, close my eyes and just go. It's really, you have to think about what are the terrestrial conditions, what's happening up on Maunakea, and is that allowing you to observe? And Maunakea is a very magical place. It's a very dramatic place. It changes all the time. There's nights that I've gone in thinking there is absolutely zero chance I'm going to get any meaningful photons from outer space tonight. And like that, it changes and everything opens up and you have a beautiful night. And it goes the other way sometimes too. It's actually usually to the positive. So it's usually a fairly kind place. Unfortunately, not these 4 nights. And so the other screens are instrument monitoring software. If we were taking observations, the red square there at the top right, the orange square there down at the bottom left, those would be images either that we've just taken or that we're analyzing and trying to understand what we're seeing. So there'll usually be like a kind of live feed where it's like, okay, you've taken an image, here's the image that we just took, here's the next image, that sort of thing. And then you can go a little bit slower with another screen that says, oh, okay, I want to analyze, I want to see, oh, how bright is this thing? How bright do I expect it to be? Oh, that means there's some clouds coming out, or the moon is brighter than we, expected, or is, something is different than what we expected. So we might need to take a longer observation, or oops, we're not in the right place. The sky is huge. We're looking at like, so the field of view of MOIRCS is something like 3 arc minutes by 7 arc minutes. Actually, in your picture, was it the full moon? The like X-ray Orion picture, was it the full moon?
Yeah.
Yeah. Okay, so full moon's like 30 arc minutes from what I remember, something like that. And so this is like, yeah, 1/4 of a full moon across on the sky, in one direction, and 1/8 of a full moon in the other direction. And so that's not a huge amount of sky. Like the full moon, yeah, it looks big on the horizon, but up in the sky, it's like, it's a big ass sky. So like, I mean, the moon doesn't take up a whole, a whole big fraction of that. And so this is even a smaller fraction of that. So it's really hard, maybe to point in the exact right direction. And usually the precision of pointing telescopes is much better than this, but you may not be precisely where you want to be. And so looking at these images, you can actually say, oh, that I recognize that galaxy should actually be over here on our picture. And so we need to move things just a little bit to make sure that that's there. And for imaging like this, just taking pictures doesn't matter so much, because like, okay, fine, we just have to move. I mean, if the galaxy is just a little bit, towards the edge, it's probably not going to matter because it's still a fairly large field of view. But when you put slits, like Ekta was showing before, so when you're really concentrating on, particular galaxies, and you're just allowing just the amount of light that you need to get, kind of get that specific information on that galaxy. If you're off by a little bit, that can be really, really problematic. And so monitoring that over time is actually one of the biggest things that, we have to stay vigilant about on the telescope, because first of all, you want to make sure you're pointing in that direction, and you have all these ways of assessing that beforehand. You make charts, and you do your homework beforehand, so you know when things go wrong, what to do. And then if you're like, okay, great, we're pointing in the right direction, all good, ready to go, let's start taking observations. Those observations for us usually take about 5 hours, something like that. So we're on a particular observation for 5 hours. So we're just sitting there, and we're taking it, and the telescope's tracking, and the sky's moving and everything like that. And if everything works perfectly well, then great, then you're fine. But sometimes things slip, or actually the atmosphere changes the apparent location of objects as you move in the sky. This is called differential atmospheric refraction. And so things can actually move, even if you're tracking at the same rate as the sky, things can actually move enough in your slits that you have to make a compensation for this. And so we monitor things over time. Like, so on March 29th and 30th, when we do Shadow of the Scientist sessions with Keck, we'll show monitoring software that we use, because of course we'll be on a clear, cloudless, beautiful night. We'll show the monitoring software that we use. It says, oh, okay, this particular object, it's starting to drift off. It's starting to drift off. Okay, let's pause. Let's check the telescope. Let's repoint it a little bit. Okay, it looks like we're good. Okay, let's keep going, and so on and so forth. So this is really, really important. And so some members of our team will be completely dedicated to making sure that things stay where they should be. I don't know if anybody, I'm just talking here. I'm delirious. It's like 11:20. So if anybody else wants to jump in, feel free.
Oh, it's great. It's great.
I'll add just, this top window is all about the telescope, and then the actual camera, we can adjust what filters are in it, all kinds of setups of the camera and things like that. So this is an imaging camera. It's pretty straight. Well, we are using it in imaging mode. It can do spectroscopy as well. In imaging mode, basically we just say, put in this filter, and there's a motor that puts in the right filter, returns a filter wheel, and then how long to expose, and you go. But many instruments are more complicated and might have 5, 10 more moving parts that you need to control and set up. So you'd spend a lot of your time ensuring that you're setting things up correctly. So often, like on Keck, if we were observing, we would be controlling the camera and changing its filters and moving all the motors remotely in the camera. and then there's a telescope operator who's driving the telescope and pointing it. So we would be using, in the case of MOIRCS, the window that's here in the bottom right, and there might be others as well that are similar, where you control the setup of the camera. It's not like your iPhone camera or something that you used to just, you just press a button and you click, or even like your DSLR where you turn a couple of things or adjust the exposure or the f-stop or something. There's a lot of moving parts. And we're close to our end time of 11:30, so I put a link into the chat of one of my favorite videos of Maunakea for those who've never seen it.
It's stunning, absolutely stunning, Roy. And I mean, I'm definitely going to share it with other people.
Have you not seen this one before?
I've never seen this one before. No. I am grateful to have had the privilege of being on Maunakea many times and working there on the summit and at the Viz, but to see this kind of view all together, I can't believe I haven't seen this before.
Yeah, Sean Goebel was one of our PhD students who got his PhD from the Institute for Astronomy, but he does astrophotography and other kinds of photography and lots of outdoors like hiking and camping. So he went up many times to Maunakea and set up cameras at various strategic vantage points and just had them take pictures throughout the night and then, make a time lapse and then set it to music. I actually find it very, I don't know, enthralling, something. It's like inspirational. I love this video. Play it with the sound up. Does anyone else have questions for us before I think, what do you think, Brian? We say good night, good morning, whatever time it is for people.
I would like to say thank you all for Brian and Roy and Ekta. I'm not sure if you contributed to the pre-activity. That was actually really, really helpful for me to go through. So thank you for that. And I certainly really do appreciate all the insights that you, all three of you have shared with us. Thank you so much. And I appreciate also the conversations and the questions and comments that have been shared. I really appreciate that engagement.
Thanks, Jamika. We appreciate you too. Thank you for coming on. It's such an odd hour. I think it's the oddest hour, at least of the four of us. So it's been great to have you here for this session and to stay for the whole session. And I'm really looking forward to us getting some actual observations together later this month.
I am too. Actually, in the observations for later this month, will you be looking at the same targets?
Yeah, so yeah, for people that are interested, there's a sign up for, no, actually we don't have to sign up yet, but we will soon for the observations that are coming up later this month. So the 29th and 30th of March, it's going to be around the same time, 9:30 to 11:30 Hawaii Standard Time. And so, yeah, so we're looking, so we have Subaru for the first half of the night. We also have Keck 1 for the first half of the night, where we're going to be using an instrument called MOSFIRE. So this is, oh gosh, okay, I have to do this on the fly. Multi-object, spectroscopic, I don't know, shoot, that's embarrassing. Something infrared explorer. I wonder what the F stands for. Anyways, so yeah, so this is a multi-object near-infrared spectrograph on Keck. So that's basically what Ekta was showing, where you put down slits on particular galaxies. And so that's a little bit different, as Ekta mentioned, because Those are like maybe per observation, we get something like 30 galaxies that we can target. And so we're getting very specific information on these 30 galaxies, as opposed to MOIRCS, where we're getting, an image of this kind of like quarter of the full moon. And so we can see all the objects in that particular part of the sky. So the MOIRCS observations are a little bit more exploratory in some sense, because we're just trying to cast a wide net and see what comes out. The Mossfire observations are also exploratory in some way, but we're targeting particular types of galaxies, and we're going to get a spectrum of each one of the galaxies. So we're going to get lots of color information on these galaxies. And why we want to do this is, again, to determine distances, but to determine more precisely the properties of those particular galaxies than you can do with just a color imaging. So we will be targeting the same structure that we were planning on targeting this evening with Subaru that time. And so that system is actually one of the most massive structures in this kind of catalog of structures that don't seem to have a whole lot of galaxies in them. So really interesting target. It's actually a massive structure that has some galaxies right next to a massive structure that doesn't have galaxies. And so we're trying to compare and contrast those. And then for Mossfire, we're going to be looking at a potential supercluster of galaxies. So this is a cluster of clusters. And we're trying to pick out the precise properties of galaxies which inhabit this superstructure. So we're looking at different parts of the superstructure, mapping it out again, and then trying to determine how massive the galaxies are, how many stars they're forming, whether they have black holes, that sort of thing. Oh, come on, 4? It's 4, that's what the F is? Ah, that's cheating.
That's Astro.
Boo. Okay.
Wow.
I quit. Yeah, we didn't talk about acronyms, but astronomers can be a little bit weird with those. C3VO, come on.
I thought that was so cute, C3VO.
It is actually cute. Yeah, it's super cute. Yeah.
Can I ask a really quick question, just in general, about galaxies in this last minute or so?
Yeah, of course.
So we're learning so much from JWST, and of course, recently we've had quite a few galaxies from very well-formed galaxies, large galaxies, even the size of our Milky Way galaxy, found very much earlier in the universe than was expected. Can you speak to that? I know that's very recently out, and I don't know if you have any insights, but I'd be curious to hear what anyone has to say on that, because it was just shocking to see such well-developed large galaxies so early on in the universe.
Before Brian may be the best to talk about this, but I do want to say that if you read the title of the paper in Nature, the word candidate is in there, which means we do not know. They look like they may be. So along with that uncertainty, it is the case that people have been finding what seem to be massive galaxies at higher and higher redshift at earlier and earlier times in the universe. And when you only find 1 or 2, then, oh, well, they're just the super weirdos. But as people are finding more and more, I do think that, as we've talked about, like simulations that try to predict how galaxies form, don't do very well at making those. So I do think there's something missing, but Brian's probably more knowledgeable, certainly more knowledgeable about that than me.
Yeah, I mean, I'll just comment a little bit on this. I mean, so JWST is very exciting, very, very, very exciting. There's so many super cool results that are coming out. It's seeing wavelengths of light that we have seen before, but we haven't had the level of precision, resolution, not even close, not even remotely close. It's a dramatic change in our ability to see the universe. There's no denying that. That being said, with all that excitement comes excitement can sometimes not be great for rigor, and it can overwhelm rigor. And there's a race because I think for positive reasons, a lot of the data that are taken aren't what's called proprietary. So they're just observations that are taken that everybody can use in the scientific community. And there are people that the teams of people that have proposed for these observations that they're very interested in getting some substantial publication out of them. So there's a race to get exciting papers out on exciting objects, and it can be that the level of scrutiny of those results, that analysis, is not really quite there yet. And you see this a lot of times when we have paradigm shifts in astronomy. The image I just showed on the pre-session activity from an instrument called WIF-C3 on Hubble. This is something, an instrument that they actually flew up. They had a space mission, they installed WIF-C3. This is around 2012, I think. And then some observations were taken, and this was never before seen light at this kind of resolution. And there was so much activity, so many things happening, and people got really excited about some results that turned out over time to not necessarily be true, or they were partially true, but they weren't. They were kind of major exceptions to the rule, right? And so a lot of these papers that are coming out, they're specialized objects, and even worse, they can be candidates, right? So they're not confirmed galaxies at a given distance. And so one has to take with a large grain of salt these claims, because it really does matter. Like for the sizes of galaxies, for example, depending on how you measure sizes of galaxies, you can actually get extremely different answers based on the shape of a galaxy. So suppose a galaxy looks like, and probably Ekta is even better to talk about this than me, but suppose a galaxy looks like elliptical or something like that, right? It's very regularized shape. It's something that we can understand. You can parameterize it, meaning you can say like it's an ellipsoid. So there's some formula you can put to that, right? You say, okay, I can make a football shape with a formula, right? And then I'm going to apply that formula to a galaxy, and I'm going to get out the semi-major axis, the semi-minor axis, and I'm going to call that the size. And that's a reasonable approximation for those types of galaxies. But when you get these like really crazy, knotted, irregular galaxies, if you try to force an ellipsoid shape to that, you're going to get really crazy answers. And so you can do what's called non-parametric sizes. So you can, you don't necessarily have to have a formula, but you can kind of measure the distribution of light. And you can say, oh, okay, well, about half the light is contained within, this distance away from the center, what we call the center of the galaxy. But that's going to give you a very different answer in these irregularly shaped galaxies than, for example, a galaxy that's ellipsoidal. And so really your analysis tools matter a lot for this. And it's the same thing goes, like there's a lot of papers that are coming out that are saying what we call the metallicity of galaxies. So the amount of elements, heavy elements in a galaxy, and heavy in astronomy is anything that's not hydrogen, basically. So anything that's not hydrogen. And so as stars are born and then they die, most of the light elements come from the Big Bang, and then stars are born, die, and they deposit heavier elements into the gas and dust that makes up a galaxy, and then those make new stars and so on and so forth. And there's an evolutionary process whereby there's a chemical enrichment of the galaxy. And so you would expect, as a very early part of galaxy formation, there's almost no metals. Everything's like the chemical composition of the Big Bang. And then over time, things get enriched by oxygen and carbon and all these metals that are made either in the cores of the stars or when they go supernova. And so people measured the metallicity, what's called the metallicity, so the amount of carbon, oxygen, iron, all these things in galaxies with JWST. And we have Journal Club at Gemini North, Jamaica, you come to very often and present very often in. And I did a comparison. So basically I made a study of 5 different papers that took the same data and looked at the metallicity of a set of galaxies. And so one came up with the conclusion hey, these things seem super evolved. Another came up with the conclusion, hey, these galaxies don't seem evolved at all. They don't seem to have a whole lot of metals. That's interesting. And then the other three were kind of somewhere in between. And it all had to do with the way that they analyzed the data. And they were kind of like saying like, oh, you're not supposed to do that way of analysis. You do this other way of analysis. And eventually we'll come to a kind of consensus answer. But it's really hard to tell right now who's right and who's wrong. But it's true that there are extraordinary properties of galaxies that in the very distant universe that JWST is picking up. That's undeniable. And it's going to challenge our models, as Roy said, and it's going to challenge our understanding of galaxies. But one thing that's really important to keep in mind beyond everything that I just said is that you find one galaxy, that's not a sample. You really have to make sure that that is within. That's not just some statistical aberration. That's not just some crazy oddball. That isn't that you still have to account for that in your models, but it may not be the norm. And so trying to make extrapolation from one or two or three sensational objects is not really astronomy. It's kind of just more sightseeing.
Thank you. I really, really appreciate those insightful responses. And Roy, you're absolutely right. It does say candidate, right? So those will require follow-up observations. Thank you for pointing that out here.
But of course, that's the journal article title. Once that makes it to the news, that word gets lost. So that's if you read it like on CNN or even New York Times or something, take it all with a grain of salt.
Oh, you're right. I saw the paper. But you're right. I was grabbing onto the major parts of that was really exciting and just kind of left off that word in my mind. But you're right to point that out. I really appreciate that. You all, I was just having some conversations in the chat. These sessions are just so stimulating and exciting for me personally, as I'm still learning and working on my studies. And so I really, really appreciate all of you. Ekta, Brian, Roy, thank you for your time and for going a little bit over. And I do apologize. I do want to be respectful of everyone's time. And for those of you who are still with us, we so again appreciate you being with us. And I think Roy dropped his email in the chat. Feel free to email us. You have on the Shah the Scientist website a general email that you can contact us at too. So please feel free to use that. And we look forward to having you again in our upcoming sessions. And I will leave the last few words with Ekta, Brian, and Roy.
Yeah, I also want to say thanks so much, everyone, for coming. This was really awesome. Like while we didn't take any observations, this was really great session. And I think we also had a great fraction of people sticking to the end of the session. So thanks so much. I really appreciate everybody.
I feel the same exact way.
Oh, yeah. Yep.
This has been great. And yeah, it's helped as a salve to the wound of not observing. I think this has just been super exciting, and I love talking about this kind of stuff. So thank you for joining and for the stimulating conversation.
Yeah, and great questions. Join us at future sessions. Tell your friends. And when the weather is good, it's more exciting because we can actually show you what we're taking pictures of or taking spectra of. So it's a little more easy to understand what's actually happening. But everyone have a good night, good morning, good evening, whatever time it is where you are. It's fun talking to people all over the world, from all over the world.
It sure is. It sure is. All right. Mahalo nui. Aloha.
Aloha.
Good night.